Hello, welcome back to KO Math. Today we're going to knock out this problem about finding derivatives of functions. To find these derivatives, we need the most powerful tool in computing derivatives, which is the chain rule. But before I show you how to solve this problem, let us first recall our basic differentiation formulas and show how do we use these formulas together with the chain rule to compute for the derivatives of most functions, if not all. Here are the basic differentiation formulas. Usually you're given these formulas in terms of x, like derivative with respect to x of a constant c is equal to 0, derivative with respect to x of x to the n is equal to n, u to the n minus 1 for any real number n. But here, let's use u instead of x because of course we can replace the x by t by any variable. Okay, as long as your function is a function of that variable. So here are formulas. So it tells us that the derivative of a constant times a function is equal to constant times the derivative of the function. Derivative of a sum equal to sum of derivatives. Derivative of a difference is equal to difference of derivatives. And this is the derivative of a product. So it's a sum of two terms. Just take the derivative of one factor at a time, and then you have to remember this formula for the derivative of a quotient. And you still have here many derivative formulas. And it is very important that you remember these formulas as quick as possible if you want to be successful in any calculus course. If you want some tips on how to remember these formulas, watch my other video. The link is given in the description below. Let us now recall chain rule, which is for me the most important and the most powerful tool in computing derivatives of functions. So it tells us how to find derivatives of a composition of two or more functions. So let's say if we have a composition of two functions, so the derivative of this with respect to x is just equal to f prime evaluated at g of x times g prime of x. So we compute the derivatives from the outside to the inside. So first we take the derivative of f and we evaluate it at g of x and then multiply that by the derivative of the inside function times g prime of x. So another way to write this chain rule using Leibniz notation. So if you know that your y is a function of u and u is a function of x, then to compute for the derivative of y with respect to x, just compute first for the derivative of y with respect to u, so that is dy over du times the derivative of u with respect to x. And this can be extended to composition of three functions, four functions, and so on. So if we have three functions here, so the derivative with respect to x of this composition is, again, we start from the outermost function. So take the derivative of f prime, evaluated at this input, times the derivative of g evaluated at this input, and then times h prime of x using Leibniz notation. So if we know that y is a function of u and u is a function of v and v is a function of x, to compute for the derivative of y with respect to x, just multiply the derivatives of y with respect to u and then the derivative of u with respect to v and the derivative of v with respect to x. Now let us combine our basic differentiation formulas with this chain rule. If we do that, we'll obtain the following. So we have here our differentiation formulas with the chain rule. So here, when we take the derivative with respect to x of u to the n, if we know that u is a function of x, so by chain rule, first we take the derivative of y, so just think of u to the n as your y. So first take the derivative of y with respect to u, so that is nu to the n minus 1 times the derivative of u with respect to x. And also, derivative with respect to x of a to the u. So think of this as your y. So you first take the derivative of this with respect to u, that is a to the u ln a, and then times the derivative of u with respect to x. And you'll obtain the other formulas using this chain rule. Okay, first take the derivative with respect to u, so you use our basic formula. That's the reason why I wrote the basic formulas in terms of u instead of in terms of x. So first take the derivative with respect to u. So here you have 1 over u ln a, and then times the derivative of u with respect to x. So notice here that if we take the derivative with respect to u instead of with respect to x, then x will be replaced by u. So this will be du over du. And you'll go back to our original basic formula, which is nu to the n minus 1. So also, if you replace this u here by x, so in this case, it will be derivative with respect to x of x to the n. This du over dx here, derivative of u with respect to x, will also be equal to 1. And you'll get nx to the n minus 1. Again, it's the basic differentiation formula. We can now solve our problem using these differentiation formulas with the chain rule. So differentiation is much easier than integration because as long as you know your differentiation formulas with the chain rule, you'll be able to find the derivative of any function that will be given to you. Also, keep in mind that we don't have formulas for derivatives of powers of trigonometric functions, powers of inverse trigonometric functions, powers of logarithmic functions. So if you're given like a derivative problem, finding derivatives of powers of these functions, then you don't have a choice but to use the first rule here, which is derivative of a function raised to a power. So you'll be needing this rule and probably a combination of this rule and these formulas. Let us now compute derivatives. So let's try to compute for the derivative of this first function, f of x equal to square root of x raised to 4 plus 1. We don't have like a derivative formula for nth roots, but this is actually a power of x raised to 4 plus 1. So we can write it down as a power of a function. So you may think of this one. You need to recognize the form of your function so that you'll know which formula are you going to use to compute for the derivative. So this is a power of a function. So this is like u raised to n. So that means we need to use the power rule, and in that case, to compute the derivative, so you bring down the power, subtract 1 from the power times the derivative of u with respect to x. So just think of this one here as what? U raised to 1 half. So when you compute for the derivative of u raised to 1 half, that but you're computing for the derivative with respect to x, first you compute for the derivative with respect to u, and that will be 1 half u raised to negative 1 half, and then times the derivative of u with respect to x. So the formula that we used here is again derivative with respect to x of u raised to 1 half is again first we take the derivative of u raised to 1 half with respect to u, so that is 1 half u raised to negative 1 half, but don't forget to multiply because using chain rule times the derivative of u with respect to x. So again, this is our u here, okay? And this is our u, which is equal to x raised to 4 plus 1. So if we continue, we still have to compute for the derivative of this one, but that is very easy. So the derivative of this is derivative of a sum is equal to sum of derivatives. So the derivative of the first term is 4x cubed, bring down the power, and subtract 1 from the power. And the derivative of 1 with respect to x is 0, so we'll get this one. And we can write this in simplified form this way. no negative powers, so you'll get here 4 times 1 half is 2 x cubed, and then this x raised to 4 plus 1 raised to negative 1 half. When you move that to the denominator, the power becomes positive 1 half, and you may write it in radical form, square root of x raised to 4 plus 1. Next function, so let's find the derivative of this g of x here, which is the power of this quotient, okay, and the exponent is equal to 10. So it is clear here that we need the power rule with the chain rule. So we need to use the derivative with respect to x of u to the n equal to, again, bring down the power, subtract 1 from the power times the derivative of the base with respect to x. So this is our u, this quotient here, it is our u. So the derivative will be 10u to the 9 times the derivative of u with respect to x. But this is a quotient, and we already have a quotient formula for derivative. So that is like low the high, so that is denominator times the derivative of your numerator, which is a 3x squared minus high, that is x cubed plus 1 times derivative of low, so that is x cubed minus 4 all over low, so that is the square of the denominator, okay, which is equal to negative 15x squared over this one when you simplify it. So there is actually a fast technique in computing for the derivative of this function if it is in this form. Okay, so I'll show that one in my future videos. So here, so we can now write our answer as we can multiply this negative 15x squared by 10, you'll get negative 150x squared. And then we distribute this power to the numerator and denominator, and we'll get here x cubed plus 1 raised to 9. And then since we have here x cubed minus 4 raised to 2, so 2, and then the plus 9 here, you'll get the denominator x cubed minus 4 quantity raised to 11. Next problem, so let's find the derivative of this y here, which is equal to this product. So here, since it is a product, so we need to use the product rule, okay, for differentiation. So how do we find again the derivative of a product? It is sum of two terms, and we can get the terms by just taking the derivative of one factor at a time. Okay, so we can get here this first term times the derivative of the second term plus the second term times the derivative of the first term. And how do we take the derivative of this one? It is like a function raised to a power u raised to n. So to find its derivative, we bring down the power and then subtract 1 from the power times the derivative of the base, the derivative of u with respect to x. Okay, and then this one here, we apply the same rule. We bring down the power, so that is 4, subtract 1 from the power, so it becomes 3 times the derivative of the base, which is x cubed plus 2x squared minus 1. Now, these are just polynomials, so it's very easy to compute for the derivative. So the derivative of 5x squared is 10x, and the derivative of 3 is 0. So that will be 10x. And the derivative of x cubed is 3x squared plus derivative of 2x squared is 4x, and then minus derivative of 1, which is equal to 0. And we may write our answer this way, so we just multiply this 6 and 10x, we'll get here 60x. And this 4 here, we can multiply it to this factor, we'll get 12x squared plus 16x. Now let's find the derivative of this function, y equals 2 raised to sine of x squared plus tangent of e raised to x cubed. Since this is a sum, we know already that the derivative of a sum equal to sum of derivatives, so we just have to find the derivative of each term. So here, what formulas do we need? Since this is in the form of a constant raised to a function, we need the formula for a raised to u. And then this is tangent of a function. We need the formula for derivative of tangent u. So if we use those formulas, we'll get here derivative of a to the u is a to the u, you just copy the function, times ln a times the derivative of u, the power, with respect to x. And then derivative of tangent u is secant squared du times the derivative of u with respect to x. And we still have here the derivatives. So let's compute for these derivatives. Now we want to find the derivative of sine of a function of x. So we need to use the derivative of sine u. And the derivative of sine u is cosine u times the derivative of u with respect to x. But the derivative of this x squared with respect to x is equal to 2x. Now, this we need the formula for the derivative of e raised to a function, e raised to u. And we have the formula which is e to the u times the derivative of u with respect to x, which is equal to 3x squared. So if we're going to write our final answer, 2 times ln 2 is just ln 2 squared, which is equal to ln 4. And we just copy this factor here, and then we have here the x, and then times cosine of x squared. And then here, this is just a 3x squared times e raised to x cubed times secant squared of e raised to x cubed. Moving to our next problem, let's find the derivative of this with respect to t. So our variable here is t. So this is a power of secant of a function. We don't have a formula for power of a secant, but we have a formula for power of a function. So that is the power rule with the chain rule. So we need to use that rule to find the derivative of this one. So here we think of this function as function raised to a power. Okay, so we need to use the formula for derivative of u raised to n. And the derivative is bring down the power, subtract 1 from the power, times the derivative of the base with respect to t in this case. Now, what is the form of our function? This is in the form secant of a function. So this is secant u. So we have a formula for derivative of secant u. So we use that formula. It is equal to secant u times tangent u times the derivative of u with respect to t. Now we're left with this one, and what is the form of our function? It is cosine of a function, so cosine u. So you use the derivative of cosine u, which is negative sine u times the derivative of u with respect to t. And finally, we get the derivative of sine t with respect to t, which is equal to cosine t. Now we can write our answer. So this is negative times 2. You'll get here negative 2. And then you have 2 copies of this one here. So you can write this down as secant squared of cosine of sine t. And then you have times this expression. And then times sine of sine t. And then times cosine t. Next problem, so let's find the derivative of this y, which is equal to this difference raised to 5. So it is clear that we have to use the power rule with the chain rule. So when we take the derivative of both sides with respect to x, so we bring down the power, subtract 1 from the power, times the derivative of the base with respect to x. And now we have a derivative of a difference. So this is equal to difference of derivatives. So the derivative of sine x is cosine x, and then minus, so this is a power of cotangent root x, square root of x. So the derivative of this, we have to use again the power rule with the chain rule. So we bring down the power 2 and then subtract 1 from the powers, it becomes cotangent square root of x times the derivative of your base. Your base here is cotangent square root of x. So derivative of cotangent square root of x with respect to x. Now, what is the form of this function? It is cotangent of a function. So we need to use the derivative of cotangent u with respect to x. And the derivative is equal to negative cosecant squared u times the derivative of u with respect to x. Now we've written square root of x in terms of rational exponents. So we write it as x raised to 1 half, so that we can easily apply the ordinary power rule. So the derivative of this is you bring down the power 1 half and subtract 1 from the power. So that will be negative 1 half. So we're done with computing the derivatives. So we can now write our final answer as this expression. Okay, 5 times this raised to 4 times the quantity. So you have here cosine x, and then negative 2 times negative times positive 1 half. So that will give you positive 1. So that will be cotangent of square root of x times cosecant squared of square root of x all over. So this one, you can write it down as square root of x. Now let's find the derivative of this y, which is equal to 5 raised to 4 raised to x squared. So since this is a constant raised to a function, we need the formula for derivative of a raised to u. And the derivative of a raised to u is just copy the function times ln of the base times the derivative of the exponent, which is the exponent of 5, which is 4 raised to x squared. And again here, we apply that rule to compute for the derivative of this constant raised to a function. So again, you copy the function and then times ln of the base times the derivative of the power, which is equal to x squared. So the derivative of that is equal to 2x. So therefore, the answer here will be, so you have here ln 5 times ln 4 times 2 becomes 2 ln 4 is the same thing as ln of 4 squared, so I can write that down as ln of 16, and then times x, and then times this expression times 4 raised to x squared. Moving to our next problem, so let's find the derivative of y, which is equal to sine inverse of ln of cosecant x. So what is the form of our function? It is sine inverse of a function, sine inverse u. But we already have a formula for derivative of sine inverse u, and that is 1 over the square root of 1 minus u squared times the derivative of u with respect to x. Now, what is the form of this? Ln of a function, and we already have a formula for derivative of ln u, and we use that one, that is 1 over u times the derivative of u with respect to x. And finally, using an ordinary formula, derivative of cosecant x is negative cosecant x cotangent x. So we can write our answer. So this times 1 over cosecant x, we cancel the cosecant x. So we're left with negative cotangent x over this denominator. Next problem, so let's find the derivative of y, which is a function of log base 4 of tangent inverse x. So again, applying chain rule. So it is very important to understand the chain rule completely. So here we take first the derivative, okay, of the outer function evaluated at this one times the derivative of the inner function. So derivative of log base 4 of tangent inverse x. So since we already have a formula for derivative of log of a function, okay, at any base, so we use that formula. So it will be 1 over ln a, our a is 4, and then times u, okay, tangent inverse x times the derivative of u with respect to x. And we also have a formula for derivative of tangent inverse x, which is equal to 1 over 1 plus x squared. So therefore, we can write our answer, and it depends on f prime. Okay, so this expression times 1, so it's equal to this expression divided by ln 4 times 1 plus x squared times tangent inverse of x. Moving to our last problem, so let's find the derivative of this function. So you may use here derivative of a quotient because we already have a formula for derivative of a quotient, but I think it's better if we write this down as a power of f of x minus g of e to the x. So we move this radical to the numerator and we can write it down as this expression raised to negative one-third. So it is a power of a function. In that case, we can use the power rule with the chain rule. So when we compute the derivative, we bring down the power, subtract 1 from the power, so that is negative one-third minus 1 is negative four-thirds, times the derivative of the base with respect to x. And the derivative of a difference is equal to difference of derivatives. So this will be f prime of x minus, again, you apply here chain rule because g is a function of a function. Okay, so first take the derivative of g evaluated at e to the x times the derivative of the inner function with respect to x. So that is again chain rule, but the derivative of e to the x with respect to x is e to the x. So therefore, our final answer is this expression times negative 1. So you'll get negative f prime of x plus, okay, you have here uh, e to the x, okay, times g prime of e to the x. Okay, and all over you have here the 3 times this one. Okay, but you move this to the denominator, so you change the powers, it becomes positive four-thirds. Okay, that's it for this lesson. I hope that you can now easily find the derivative of any function. If you enjoyed the tips that you learned here, please don't forget to hit that like button below and share this to your friends. I release new videos every week, so make sure that you subscribe to my channel to learn more strategies and tips in math. Again, this is Dennis of KO Math. Thanks for watching and see you in my next video. Bye bye.